Alright, welcome to AP video 15.6. Here we're looking at doing calculations of weak strong titrations. That's one of the main objectives, find the pH at any point during these kind of titrations. Understand the equivalence point and halfway equivalence point and how they relate to these particular titrations, and also analyze the curve for this type of titration and some of its important features. I'm going to fly pretty fast this one. It's building off the last one, trying to show you some similarities and differences. Here we go. Weak strong titrations. A weak strong refers to a weak acid being titrated by a strong base, or vice versa, which would be a weak base titrated by a strong acid. The net ionic equation for, and I'm going to cross off the word all here, for weak strong titrations is, well, it depends on what your combination is. If you have a weak acid titrated by a strong base, it would look like this. HA would be a weak acid. When it's titrated by a strong base, hydroxide, the products are going to be water and the conjugate base. And then from there you would do the stoichiometry in a Rice table to show how these two things react. If you had the reverse, it would be a weak base titrated by a strong acid. Weak base would be B in general, reacting with a strong acid, which is now H+, and the products here would be BH+. And with this, again, you would do a Rice table and do the stoichiometry between these two and see who the limiting reactant is and so forth. Whenever we do weak strong titrations, the first part is to see the stoichiometry and then really determine what's left over. Do you have HA left over, hydroxide, A-, H+? What's left over tells you what kind of problem you have. If you just have HA left over, that would be a weak acid. If you had just hydroxide left over, that would be a strong base. If you have just A- left over, that's a weak base. If you have just HA left over, that's going to be a strong acid. If you have a combination of HA and A-, that's going to be the greatest equation in the world. Okay? So always do the stoichiometry first and ask yourself, what's left over? Okay, please consult your Titration for Dummies handout, the one that's the weak strong, as we go through and do these problems together. So in practice problem number 3 here, we're doing a titration with 0.2 molar sodium hydroxide, that's the titrant, and we're going to take 24 milliliters of this weak acid, per hypochlorous acid, and titrate it. The first thing that wants to do is calculate the initial pH before we add anything. So ask yourself, what do you have? All you have right now is 24 milliliters of a weak acid, and when you have a weak acid, you go right to the weak acid method of solving. So that means you can do a Rice table if you'd like to, and in your Rice table we'll have our weak acid, which I'm just going to call HA because we're lazy and we like the shortcut, breaking down into H+ and A-, and all weak acids will go from their initial concentration, whatever it is, eventually down to X of H+ and X of A-, and we are going to subtract X from this amount. So a weak acid problem is always X squared equals the initial concentration minus negligible X equals the Ka value, in this case 3.0 times 10 to the minus 8th. By multiplying by 3.5 and then taking the square root of all that to solve for X, X ends up equaling 1.0 times 10 to the negative 4th, about that, molar. And this X here equals H+, so this is the molarity of H+. And then by taking the negative log of this, we can find the pH, and the pH is equivalent to approximately 3.99. Alright, so our initial pH of our weak acid is 3.99 before we add any sodium hydroxide. Okay, up next we actually start adding the hydroxide now. So we are adding 5 milliliters of this 0.200 molar concentration of base, and we're going to add it to 24 milliliters of 3.500 molar HOCl. So whenever you add acid to base, remember it's stoichiometry first. Okay, when you ever add an acid to a base. Well, these 24 milliliters times this concentration here ends up being a millimole amount, and that's 8.4 millimole. That's going to be our millimole of acid we're going to work with all the way through our problems here. Just a quick reminder, molarity equals millimole divided by milliliter. So if you multiply milliliter by molarity, you get millimole. And the reason we work with millimole is because 8.4 is a lot more fun to work with than 0.0084. So that's why we work with millimole. So stoichiometry first, get our rice table going, and we're going to have our HA now reacting with hydroxide, and they will react to produce the water, which we don't care about, and the A- conjugate base ion. So start with your millimoles. We have 8.4 millimole of HA, and this 5 milliliters and 0.2 millimoles, when you multiply those together, you end up with 1 millimole of base being added. So this is the limiting reactant, so we subtract that from both, end up with 7.4, nothing, and we have none of this A- to start with, but we just gained one of it. And here's the kicker. This is why it's the greatest equation in the world. Whenever you have those two things present, you can just go right to that equation. So the equation is pH equals pKa plus the log of the base component, A-, over the acid component. So pKa here is going to be the negative log of the Ka value, which was 3.0 times 10 to the negative 8th, plus the log of the base, which is 1, over the acid, which is 7.4. And remember, we don't need to convert back to concentration here, because we divide both of them. It's the ratio we care about overall. So it's going to probably be important to know, because we're going to do this a lot, as you'll see in a little bit here. That ends up being 7.2. That's the pKa. The pKa is 7.2 for this particular problem because of the Ka value. And plus this portion here, I think, is approximately 0.87. So when you add those together, we get a pH of 6.65. Alright, so in this particular problem, the stoichiometry results in having HA and A- present, which means you go to the greatest equation in the world, the Henderson-Hasselbalch equation, and when you plug and chug, you get 6.65 for your pH. Now the next few problems here are going to be very similar. I will work out letter C here, but I'd like you to pause and try to do letter C. It's very similar to letter B, but just with a different amount of base being added. When you're done, go ahead and unpause to see the answer. Okay, when you work this one out, 15 milliliters times the concentration here ends up with a millimole amount of 3. So in our rice table, we'll have 3 millimole of the base. Our HA millimole doesn't change. We just always, initial amount is 8.4 in this problem. The hydroxide we just calculate is 3. And we're going to make water and A-. We don't care about water, and there's none to start with. So hydroxide is the limiting, so you subtract it from both of these. We gain it on the product side. And now we have a ratio of 3 over 5.4 in the Henderson-Hasselbalch equation. So pH is equal to the pKa, which we found was 7.52 in the previous problem, plus the log of the base component, 3, over the acid component, 5.4. And when we do this, we end up with a pH of 7.27. Okay, if you didn't get that, you're going to want to do letter D and letter E perhaps. Keep doing these next two until you get them. And when you see the next two here, I'm just going to pause for the next slide so you can see the answers. But hopefully you're getting those. And then when you're done, we'll move on to letter F, where we're trying to find the equivalence point. Alright, and the answer for letter D here is a pH of 7.69. The volume of base added here resulted in 5 millimole. 5 in here is still the limiting reactant, so subtract it from the left side, add to the product side, changes our ratio now to have a more dominant conjugate base present, so 5 over 3.4, plug and chug, 7.69. Okay, if you didn't get that, make sure you do letter E now. Try that one on your own. Okay, and in letter E here, the volume times the concentration is 7 millimole. 7 is still a limiting reactant. Subtract, add, end up with a new ratio of 7 of the base over the 1.4 of the weak acid. You plug this in, and we get a pH of 8.22 now. Okay, so let's look at the titration for dummies for a second here. There you are. Okay, so again, green here represents the initial, and initial you always just treat like whatever. The starting pH depends on the type of acid or base you have, whether it's strong or weak, and calculate based on that. So we already did that. We calculate based on a weak acid problem. Okay. Yellow, remember, is where the equivalence point is. And just again, a quick note: this titration curve here is not the same problem we're doing there, but it still gives a good general shape. Yellow is the equivalence point, and we'll get to that in a second here. Everything after the starting point and before the equivalence point here, all the way through this region here, it's important to write this down. The pH between the start and the equivalence point for a weak strong titration is always the HA plus the OH minus. And the HA is always the excess reactant up to the equivalence point. Hydroxide is the limiting reactant. Okay, and what happens is you result in HA being left over. You've created some A minus, or if you're doing a opposite titration, strong acid, weak base, you again have those conjugate acid base pair. And whenever you have the conjugate acid base pair here, you have the greatest equation in the world. You have that ratio of the base over the acid component here. So you're going to use the Henderson-Hasselbalch equation from every point after the start all the way to the equivalence point. Every single time. Henderson-Hasselbalch equation. Greatest equation ever. Okay, next we're going to look at the equivalence point. And when you try to get to the equivalence point, the whole point is the moles of the acid and the base are equal to each other. In this case, the millimoles of HA are equal to the millimoles of the hydroxide. Well, in this case, we're talking 8.4 millimoles. So what volume does it take to get there? Well, it's the 8.4 millimoles divided by the concentration of 0.200 molar. And it turns out the volume needed here is 42.0 milliliters of base are required to reach the equivalence point. Okay. Now, let's find the pH of this equivalence point here. Well, the first part is stoichiometry. And we already know what the stoichiometry is going to be. The HA plus the OH minus will result in the water and the A minus. And if we do a Rice table to help us see this a little more clearly here, it's 8.4, also 8.4, and they completely neutralize each other, so neither of them are left over. Don't care about water. And what we've just done here is created 8.4 millimoles of A minus at this particular point here. So stoichiometry is that we've turned all of the HA now into A minus. Okay. Now to find the pH, remember stoichiometry first and ask yourself, what do we have? Well, what we have here is a weak base. Okay, this is now just going to be a weak base problem. Okay, remember weak base problems, you need to use K something in this case, we need to use KB to solve for the weak base. Okay, now one thing to remember is that there's a new total volume. So therefore there's a new concentration. Okay, so those 8.4 millimoles we have here, we need to make sure we convert that back into concentration. And the new volume is the 24 we started with plus the 42 we added. This is in milliliters. And this gets us into a concentration of approximately, let's see here, let me back it up. Gets us to a concentration of approximately 0.127 molarity of the A minus. Okay. Now, if this is a weak base problem, all we're really doing is solving for X and a KB. So KB is going to be KW, which is 1.0 times 10 to the negative 14th, divided by the Ka of this problem, which is right here. Remember, this is how we solve for Kas, or for KBs if you have Ka. And KB here equals approximately 3.3 times 10 to the minus 7th. So set this equal to X squared over the initial concentration of 1.27 minus negligible X, and solve for X. Okay? And when we do this, remember, in a KB problem, when you solve for X X is equal to the hydroxide concentration. And the hydroxide concentration here is 2.1 times 10 to the minus 4th molar. Okay, just a quick little heads up, even I made a small mistake here. Don't forget, you multiply these together and then take the square root. I forgot that part. Okay, so when you get the square root in there, this is the hydroxide you get. Take the negative log of this to find the POH, which is approximately equal to 3.69, and then convert this to pH by subtracting it from 14. And the pH is 10.31. Alright, so notice at the equivalence point here, for a weak strong titration, the pH is not going to be 7. In this case, the pH is basic because at the equivalence point, HA has been neutralized now into A minus, so you should have a basic pH. Okay, now just so you all know, this is the hardest part. Okay, the hardest part is the equivalence point for weak strong titrations. You need to make sure you neutralize it, know your new total volume, and all those millimoles of weak base you've created, divide by the new total volume to get a concentration here. Then treat it like a weak base problem and work your way back to pH. Okay, again, we'll practice these a lot, but this is the trickiest part of all the problems. Now we're going to go past the equivalence point, and if we're going to go 5 mils past, that means we've added the 5 to the 42 it took to get to the equivalence point, which means 47 milliliters. And this gives us a total millimoles required of 9.4 millimoles at this point. So in the rice table, going right back to the beginning, HA, we had 8.4, plus the hydroxide is going to make water and A minus. And we're adding in 9.4 now. Water, we don't care. A minus is 0. So now HA is the limiting reactant. We subtract that from everything and add to the product side. And we have none of the acid left. We have some hydroxide now left over. That's the excess reactant. And we have this A minus here. Now, here's what's left over. OH and A minus. Ask yourself, what do you have? Well, you have a strong base and you have a weak base. Who's going to determine the pH? Always the strong ones. So now this weak acid that's left, or this, weak base left over, we don't care about it. You have 1 millimole of strong base, which is hydroxide. So it's a strong base problem. Get this back into concentration. The 1 millimole divided by the total volume, which is the 24 we start with, plus the 47 we just added. And when we do this, we get a concentration of 0.0196 molar hydroxide. And from that, find POH, which is 1.71. And from that, find pH, which is 12.29. Alright? So, when you go beyond the equivalence point, it becomes a strong base problem because that's what's left over, and that determines the overall pH now. So look at the titration for dummies quick. So at the equivalence point, that's when the moles or millimoles of your analyte is equal to the millimoles of the titrant. Make sure you divide by your new total volume, and you now have basically either a weak acid present or weak base present or a weak acid, depending on what kind of titration you did there. And this is the hardest part here. Okay, make sure you practice those. Once you go beyond the equivalence point, okay, the pH after that point is what's left over. Either your strong base you're titrating with, or maybe a strong acid, depending on the type. Divide by new total volume, and from there you can find either POH, then pH, or pH straight up if you were titrating with a strong acid there. Okay. All right, heading back over. Oops. Okay, so if we're gonna draw this thing out here, we start off with 0 for pH is right here, 7, 14. pH is the y-axis. Volume of base added is down here in milliliters, and we'll just go by tens. Okay, so pH started at 3.99, which is right about here. At 5 milliliters, the pH went to about here. At 15, it went to about here. At 25 was here. At 16 it was here. The equivalence point was 42 milliliters, and it was a little over 10. And at 47 milliliters it was up to here. So here's our general pH curve of a weak acid being titrated by a strong base. Like so. Okay. So a couple quick characteristics here is starts with sharp increase and then levels off. Equivalence point is another sharp increase and then levels off again. Okay. A weak or a strong titration would look more like this. It would have started lower and just gradually increases and had a sharp increase, and then it actually ends up ending pretty much the same as this other titration we're doing right now here. So kind of notice the difference there. This one just gradually increases and then increases sharp at the equivalence point instead. One really quick thing to notice here is notice how the pH barely changes through this region here. You know why? You have A minus and HA. What do we call that? Well, whenever those two are present, that's a buffer. And right in the middle here, at the halfway equivalence point, halfway between here, this is the region of maximum buffering right there, like plus or minus a pH of 1 there. pH barely changes in this region here when you're at the halfway equivalence point because the ratio of these two things are very close together, and that's when you have an optimal buffer, when those two concentrations are roughly equal to each other. Okay? Alright, last things. Why is the pH not 7 for a weak strong titration? Because for a weak strong titration, you've either taken your weak acid and converted into an A minus, which is a base, or you've turned your weak base into its conjugate acid form, which is an acid. So the pH is never going to be 7 for a weak strong titration because you've created either conjugate acid or conjugate bases. So, what do you think the pH will be if you titrate a weak base at the equivalence point? Okay, you should be saying the weak base has been turned into its conjugate acid form, so it's going to be acidic, and that means the pH is less than 7. Okay, this will probably be the longest video of the year. Hopefully made sense, and come ready to practice tomorrow.